Good evening. This is Lokavya Baskar. Here, me and Rattan Kumar are here to discuss our paper on intrusion detection system using ML for network security. Here, I'll be talking about the abstract and the introduction part of our paper as well as the limitations, and the other things will be done by Rattan Kumar. So here we go. So when we here what we have basically explained in our paper is that it talks about the realm where technology and cyber security converge. So for example, imagine a world where digital innovation intertwines with the ever evolving landscape of cyber threats, where the stakes are high and the need for robust defense measures is paramount. So this paper basically encapsulates precisely that and a call to arms in the face of relentless cyber threats. So let's start with the abstract of our paper. So here, here we have given a snapshot of a digital reality. It paints a picture of a digital age where technology reigns supreme, offering boundaries of opportunities for progress and connectivity. Yet, amidst all these innovations, there's a shadow of cybercrime. So, malicious actors exploit our interconnected networks, wielding sophisticated tools to compromise our data and disrupt our systems. So, what our abstract basically does that it serves as a clear, is a call highlighting the urgent need for robust cyber security measures to safeguard our digital infrastructure. So, now let's move on to the introduction part of our paper. Here, Um, so here what we have done is we are talking about our frontline defenders of our digital realm. That is our intrusion detection system, IDS. That is what our entire paper is based upon. So these systems stand as vigilance sentinels, tirelessly monitoring network activity to identify and thwart potential intrusions. However, traditional signature based detection methods struggle to keep pace with the ever changing tactics of cyber criminals. So, this is where the narrative takes a turn towards hope, a beacon in the form of machine learning. So, here the machine learning emerges as a game changer in the fight against cyber threats. Its ability to learn autonomously from a vast data set offers a glimmer of hope in enhancing threat detection and mitigation. By leveraging the power of machine learning, we can adapt and evolve our defense strategies to stay one step ahead of cyber adversaries. So, in this essence, our paper basically serves as a roadmap, a guide to navigate the complexities of intrusion detection and harnessing the transformative potential of machine learning in fortifying our cybersecurity defenses. It's a call to action for all stakeholders in the cybersecurity ecosystem to collaborate, innovate, and adapt to the ever-changing threat landscape. So let us remember that the future of cybersecurity lies in our hands. Together, we can build a more safer, resilient digital world, one where innovation thrives and threats are met with unwavering resolve. Thank you.
Now we're going to be looking at the different anomaly detection system classifications and the different techniques or systems involved in these IDS. So first we look at the classification, and based on the classification we'll see different techniques. So first, what is classification? So classification is like the segregation of different IDS based on the approach or based on the technique that is used in these systems. So it can be anything, it can be based on how it detects threat or what are the models used in this detection system. So first we'll be looking at the statistical anomaly based ideas. So in this there's no prerequisite knowledge or anything like that. There's no model working. We are seeing or we are monitoring certain parameters always. So let's say it's like network bandwidth or like network traffic or anything like that, protocols or something like that. So we're taking or monitoring those parameters always, and they always have to stay within a limit for a normally working network. But if it goes beyond a certain threshold or certain limit, then we can classify it as a threat. So that's how it works, based completely on statistics, not based on any prerequisite knowledge or anything like that. So an example of that attack is DDoS, a distributed denial of service attack. So this is a very common type of attack. Uh, in the previous attack, there was no need of prerequisite knowledge, but in this you need some database, a data set, which has a set of data based on the previously occurred attacks. So based on the parameters or the values, the thresholds met in the previous threats, we can classify presently occurring scenarios into either a threat or not a threat. So it's not the most accurate technique, but it is very simple to implement, and it's completely dependent on the data set. So it's not using any model to predict something new, something out of the data set. It's only searching within the data set, and then it is classifying the threat. So this is very simple as well. And then the next is the machine learning based ideas. So here is where we have a model which is implemented in the IDS. So in this also you need a data set based on the previously occurred threats or not threats. Okay, and you use all that and you find a pattern. So in the previous one there was no pattern. You're just comparing if it is the same or not. But here you're looking for a pattern, and if it is somewhat near to what was expected from a threat, then it will be classified a threat or not. And in this we can keep weights or any sort of threshold in order to improve the accuracy of the model. So we can keep tuning it based on more and more data sets, more and more epochs. So it depends on how well it is trained. The accuracy is based on how well it is trained. So these are the basic classifications of the intrusion detection system. Obviously, in real life, it's not very easy to classify a detection system just based on these three types, because mostly in real life, uh, IDS is based off. Obviously, in real life, it's not easy to classify an IDS based on just these three types, because as the cyber threats become more and more complicated in day-to-day lives, we have to create systems based on like a combination of these three types. So it's not easy to classify into this, but this is just a basic classification which will help us understand the different techniques involved. First is the Bayesian network. So this comes under the machine learning classification of the IDS. So here we are finding the probability of it being a threat. So we have different parameters for each, like example network traffic or network speed or something like that, different parameters, and we give each one a weight or a value or like a probability of how it affects the outcome. So we'll take previously taken data set, we'll divide it into test data set, and then training data set. Based on the training data set, we'll train the model, and then we'll give it like probabilities or weights or something, and then we'll use the test data set to test the accuracy of the model, and we'll keep adjusting the model in order to make it more accurate. Obviously we can see the pros. There are encoding interdependencies, predicting events. So predicting events, so it's not dependent on something which is already existing. It can predict something new. So if you're giving a new scenario which is not there in the data set, it can predict. So it's like really good at that. But there are cons as well. There's a lot of training. There's a chance of inaccuracy as well. So the next is the Markov model. So in this, it encompasses different types like Markov chains and hidden Markov models and things like that. Even in this, you're giving it a transition probability during training and detection anomalies. So in this, we have different concepts like transition probabilities, state transition matrix, emission probabilities, etc. All of these, it is very similar to the Bayesian model, but it is there are different hidden layers and things like that. Next is the neural networks. So network, obviously, if you've learned machine learning, you'll know what neural network is. It's very similar. It mimics the functioning of the brain. There are neurons and there are different layers, and that improves the accuracy of the result. So it mimics the functioning of the brain, and it is really good at parallel processing. So it doesn't depend on each layer. It can parallelly process multiple data inputs and come to a conclusion, and you can train the data set to achieve a certain result. So if it's not accurate, you can uh, change the weights or other things like that in order to achieve a certain output, and that can improve your model drastically. The con of neural networks, obviously, it's computationally expensive. It needs a lot of computing power because there are multiple neuron layers, like the main layer and then hidden layers and things like that, but that you need to implement in order to make the model run. So it is computationally expensive. Next is the fuzzy logic technique. So in the fuzzy logic technique, what you're using is you're taking a data set, like a fuzzy data set. So all of them, there are some data sets which are directly related to the model, and there are some data sets which can distract the model as well. So you have to fit the model in such a way that it can incorporate, or it can predict multiple data sets. So it doesn't have to be, or it shouldn't be overfitting the data set. If it overfits, then it cannot work for different scenarios. So that's how the fuzzy logic works. It can handle imprecise and uncertain data because it's not overfitting. It is perfectly fitted. So it can take a little bit of data which can overthrow the model, or which can confuse the model as well, obviously. But the con of this is that it can lead to inaccuracy. So it needs a lot of training and a lot of computational power, a lot of time to come to a perfect fit for the required computation. Next is a genetic algorithm. So genetic algorithm, it represents a global search heuristic. So you're giving it heuristic values, and based on that, it predicts whether, or classifies whether the given data or given thing is a threat or not. Okay, so there are again parameters and certain classification rules and heuristic values that help in classifying whether the data is a threat or not. Then you have clustering. So in clustering, we have various clustering models. One of the examples is K means. There's a K medioid, K mode clustering, and a lot of different clusterings as well, hierarchical clustering, things like that. Here, K means clustering is one example where you're taking the centroid value. Like initially, you make some assumptions. You take a centroid value. Let's say you want two groups. One is a threat and another one is not a threat. So you take a random centroid value as, in order to classify it into groups, and then you find the distance from the centroid. You can use either Euclidean distance or Hamming distance or things like that. Then you find the distance, and whichever has the lowest distance, whichever is like nearest to the centroid, you'll give that group, the group of that centroid, to this data set. And then you'll keep going through multiple epochs. You'll find multiple values in a group, and then you'll find a new centroid, and you'll update the centroids, and you'll do that again and again in order to come to a satisfiable, or like a pretty accurate model to cluster whether the model is whether the data set is a threat or not. So this is one of the examples, and these are some of the techniques involved in IDS.
So, hi. So here we are going to look again. What we are going to look at is the limitations that we have discussed in our paper. So the basic limitations that have been outlined in this paper is that it navigates the intricate landscape of cybersecurity. So it is very crucial to recognize that while technology offers boundless opportunities, it also presents a fair share of challenges and limitations. Now for the limitations, what are the basically one significant hurdle that we have encountered is the imbalanced data sets. So in the realm of intrusion detection, security threats often constitute a minority class compared to normal network traffic. So this imbalance poses a considerable challenge for machine learning algorithms, which may struggle to adequately capture the minority class, leading to a biased model that prioritizes the majority class. So, addressing this limitation requires innovative strategies to rebalance the dataset and ensure that intrusion detection systems can effectively detect and mitigate potential security threats. Furthermore, the dynamic nature of network environments presents another formidable challenge known as concept drift. So, as the statistical properties of data change over time due to emerging cyber threats, systems, or shifts in user behavior, static intrusion detection models may become outdated or less accurate. Adapting to concept drift demands the development of adaptive intrusion detection models capable of continuously learning and evolving in response to changing data patterns. So, this requires ongoing research and innovation to stay afoot of evolving threats and ensuring that the effectiveness of intrusion detection system has an impact in the real world environments. So, So another limitation that we have encountered is the challenge of feature selection. So identifying the most relevant feature from a data set is very, very critical for developing effective intrusion detection models. However, the process of feature selection is complex and resource intensive, requiring a very, very careful consideration of various factors such as feature relevance, redundancy, and computational efficiency. This limitation underscores the need for advanced techniques and methodologies to streamline the feature selection process and optimize the performance of intrusion detection systems. So, additionally, the computational overhead poses a very significant challenge for intrusion detection systems, particularly in real time applications where the timely decision making is very crucial. So, intensive machine learning algorithms may struggle to meet the computational requirements of the real time intrusion detection, leading to delays or inefficiencies in threat detection and response. So, striking a balance between accuracy and computational efficiency is very essential to ensure that intrusion detection systems can operate effectively in resource constrained environments. So finally, there is the issue of adversarial attacks, which presents a very sobering reality for intrusion detection systems. These malicious actors may exploit vulnerabilities in machine learning models to evade detection and launch sophisticated cyber attacks. So these attacks involve manipulating training data or model inputs to deceive machine learning based intrusion detection systems, leading to false negatives or misclassification of security threats. Addressing this limitation requires robust defense mechanisms and adversarial training techniques to enhance model resilience against adversarial attacks. In conclusion, while technology may offer immense promise in bolstering our cybersecurity defenses, it also presents a very formidable challenge and limitation. By acknowledging these limitations and embracing a spirit of innovation and collaboration, we can work towards overcoming these hurdles and building a safer, a more resilient digital world.